It's my pleasure to introduce Urs Frauenfelder from Augsburg. So the title of this talk is The Little Sibling of Rabinowitz Action Functional. And I guess I should just say, I think it might, you have the option of pinning his video if you want to make it bigger. So I think that might be the recommended thing to do here. If you pin it, then you can see the blackboard really well. So anyways, yeah, so thanks. So take it away.
Yeah, thank you very much for this invitation. Yes, I would like to talk about the little sibling of Rabinowitz action functional. So let us first start from something back to calculus, namely Lagrange multipliers. So suppose n is a manifold, and we have two functions, f and h, smooth functions on n. And we assume that 0 is a regular value of h. And then, as you know, then if one wants to look for critical points of f under the constraint given by h inverse of 0, there is this Lagrange multiplier functional. So this Lagrange multiplier functional, let's call it capital F. Capital F is defined on n times r, and so x tau. So I call my Lagrange multipliers tau for some reason. Lambda is not so good because we later need lambda for the Liouville 1 form. So x tau is mapped to little fx plus tau h of x. And then, as one learns in calculus, there is one-to-one correspondence between critical points of this Lagrange multiplier functional f and the restriction of f to the constraint h inverse of 0. So we have crit f. This is one-to-one correspondence with critical points of f restricted to h inverse of 0. Namely, if you have x tau, then we just forget about the Lagrange multiplier tau. Right. So this is if one looks at, so there's one-to-one correspondence between critical points. If one looks at the Morse indices don't quite agree, but they are related by a global shift by 1. So you see this Lagrange multiplier functional is a bit an interesting functional because it's neither bounded from above nor below. So if h is different from 0, tau can be everything. So it can be arbitrarily large, arbitrarily small. So this capital F does not actually attain global maxima or minima. And there is some kind of justice here, namely, if you think of, so this h inverse of 0, this lies in n, and here has codimension 1, and n has codimension 1 in R, so it has codimension 2 in n times R, and so this the Hessian, there will be one additional eigenvalue and one additional negative eigenvalue. So we have for the Morse indices if you look at the Morse index of f of x tau, this is just one more than the Morse index of f restricted to H inverse of 0 of x plus 1. So in particular, if one for the gradient flow lines, if one looks at the Fredholm index of its linearization, so the Fredholm index is given by the difference of this Morse index of it, because this is a global shift by 1. So the Fredholm indices don't change. And now, if one does Morse homology, then one also has to look at gradient flow lines. And now, where we have a one-to-one correspondence between critical points, the correspondence between gradient flow lines is not so canonical. So let's look at gradient flow lines. So to discuss gradient flow lines, we need a Riemann metric. So we first choose G, a Riemann metric. N. So if you have and then we so our Lagrange multiplier function, so this lives on n times r. So what we do, we just take the sum of the product metric of G and the standard one on R. So we look at the metric G plus GR. That's just the GR is just the standard metric on R, just multiplying real numbers together. This on n times R, and for the constraint, we just look at the restriction of G to H inverse of 0. That's it. This is the metric on H inverse. And now for the gradient flow lines. So first, what are the gradient flow lines for capital F? So for capital F, so we have some x tau. So x is smooth map from R to N, and the Lagrange multiplier is now also flowing from R to R, and the equation so if we look at the first of the gradient here of F and H with respect to G, so we have ESX plus nabla Fx plus tau nabla H of x equals 0. And if we differentiate with respect to the Lagrange multiplier, we get H. So the Lagrange multiplier is goes like ES tau plus HX. This is 0. So this is the gradient flow equation for the gradient flow of F. And now we can also look at the gradient flow equation for little f, for the restriction of little f to H inverse of 0. So in this case, we have just x, a smooth map actually to H inverse of 0, but H inverse of 0 is in N, so I write this as smooth map from R to N. And then for in the first equation does not change, so we have ESX plus nabla fx plus tau nabla hx equals 0. But then the second equation, for the second equation, we have the second equation is just we are on H inverse of 0. So we our second equation is H of x equals 0. So this is 2. So this here is the gradient flow equation for the Lagrange multiplier functional, where little x is the gradient flow equation for the restriction of f to the constraint. And so actually for case 2, this Lagrange multiplier tau is actually completely determined by x. So I didn't write it actually here in the data. So we have also a tau as dependent tau, but this we can compute directly with the help of x, and as follows. So if we differentiate the second equation here into, so h is constant 0, so we have e of es, h of x is still 0. Now we this is eh of x, esx, and now we plug in for esx the first equation into. So this gives the dh minus dh applied to nabla f, so that this I can write minus gradient of h gradient of f, and then minus tau and then hx square. And note, so by our assumption that 0 is a regular value of h, so and x is always on h inverse of 0, so that the gradient here, this is never 0, so this is different from 0, and therefore we can determine tau completely with the help of x by minus nabla hx x, and then we divide this by the norm square of the gradient of h. Good. So so there is, a long time ago I once proved that if you look at the Morse homology of the two problems, namely for the Lagrange multiplier functional and for the restriction to the constraint, they actually compute the same Morse homology up to this global index shift by 1, because as I told you, so the index of the Lagrange multiplier function is always 1 more than the index of the restriction of f, of little f, to h inverse of 0. So let's state this as a fact. So we have the Morse homology of the Lagrange multiplier function, this corresponds to the Morse homology of f restricted to h inverse of 0, at least under some reasonable assumptions. So for example, h inverse of 0 should be compact, and then f, the f is now just a Morse function on compact as a closed manifold. So this just computes the usual homology of the constraint. So this is homology of the constraint up to global index shift by 1. And so this result, when I proved this, I was using something very finite dimensional, namely I was deforming the little f in the normal directions of this h inverse of 0. That's you can, of course the critical points don't depend on the normal directions of f, but this was kind of very finite dimensional approach, because so this little f will be later on meant to go to infinite dimensions, and then this little f lives on infinite dimensional space, and then it is rather dangerous to deform it in the normal directions. And so currently I'm actually working with Joa Weber on a different approach to this, and this is more based on an adiabatic limit argument. So let me give you the formal adiabatic limit argument. Namely, what we do is, so before we looked at, here we had the metric G plus GR on n times R. And what we can do is we can make this metric epsilon dependent. So we put here in front of the R part an epsilon. So if we put here instead of GR epsilon GR, what we get is the following gradient flow line. So the first part does not change. So we have still ESX plus nabla fx plus tau nabla hx equals 0. But now in the r direction, the metric gets very weak. So the gradient is contravariant. So it gets very strong. So we have to divide here this h by epsilon, respectively. If we multiply this whole equation by epsilon, we get here epsilon es tau plus hx equals 0. So this is the epsilon gradient flow equation. And so epsilon here should be equal to 0. But then if you let epsilon go formally to 0, then at the end you for epsilon equals 0 you reach precisely we discover the equation on the constraint. So so this is current, and so if adiabatic limit would give for small epsilon a 1-to-1 correspondence between the two gradient flow. the moduli spaces of gradient flow lines, and that's current work on the progress with your behaviour. But now I would like to go to an infinite dimensional setup, so that a Lagrange multiplier functional in infinite dimensions, and this is this Rabinowitz action function. So let's go to so Rabinowitz action function. So let me assume that that we have some exact symplectic manifold. So we have m omega equals e lambda is some exact symplectic manifold. So this exactness is not really so crucial, but it yeah, it makes the notation easier. So we don't need introducing filling disks. So we have and no Novikov theory. So we have exact symplectic manifold, and we have by L, I abbreviate the free loop space of M, and then we have H, a smooth map, so the Hamiltonian. So this Rabinowitz action function. So this is this lives on L times loop space times reals to R, and it's a Lagrange multiplier functional. Namely, if we pick V a loop and tau a real number, so the Lagrange multiplier, then we what was our little or our function little f is now the area functional. So the little f is now just the minus the area function. This is the integral of the pullback of lambda. So that corresponds to a little f we had before. Then the little h we had before is now the mean value of h along the loop, and here we have the Lagrange multiplier. So this is Rabinowitz action function. And what are the critical points of this Rabinowitz action function? So let us look at its critical points. So critical points. So suppose that V tau is a critical point of H. So for that, let us abbreviate by the Hamiltonian vector field. So this implicitly like this by this condition. And then if we differentiate with respect to the loop, then if we freeze in this Lagrange multiplier, this is just usual action function of classical mechanics for tau h. And so if we differentiate with respect to the loop, so we get Hamilton equation. So we have our first equation is just so the E, this is if you differentiate area, and then we get from differentiating this tau h with respect to the loop, we get minus tau x h v. So this is 0, and then as a second equation, so we get the constraint. So we differentiate with respect to tau. So we have integral 0, 1 h of et equals 0. And so this is for S1. So this is the equation. But now you observe that so h is autonomous Hamiltonian. H does not depend on time. So by preservation of energy, h is preserved under its flow. So that means by the first equation we know that h is constant, and because it's constant, so and it's constant, its mean value is 0. So this means h is always 0. So we can replace this mean value constraint by a pointwise constraint. So a preservation of energy this is equivalent to a equals tau xhvt, and then the second equation is just we have and this is 0 for every, so for all t S1. So these two equations are actually equivalent. So what these critical points are, so we have they are on the loop space. So we parameterize the loop from 0 to 1, but here we have the tau. And now if tau is positive, you can think of this as the period of the periodic orbit. So it's a periodic orbit of prescribed energy, but period is arbitrary, can be arbitrarily large. But then, and this is a bit special in this for this action function. So this is still a bit confusing thing, is that tau can also be 0. It can also be 0. Then if it's 0, then we have just a constant here, just a constant point on the hypersurface. But it can also be negative. And if it's negative, so this means that we have a loop going backward. So yeah, that's a bit funny. So what comes out is that we're not always going forward in time, but we can also go backward in time. Yeah, and this fact that we have, that we can also go backward in time, this has a lot of strange also relates. It's kind of a Tate property. So this you can somehow think of this Rabinowitz homology is kind of a Tate version of symplectic homology, where the Tate means that you can also go backward. And yeah, and it's also, so my work of Silverg is also related to pointer duality on loop spaces. So this is a very special thing, that is how can be negative, but we can actually understand this a bit more general. Namely, let us look at the symmetries of this Rabinowitz action function. So this Rabinowitz action function is invariant under various symmetries. And so let us analyze this a bit in more detail. So this free loop space is kind of a fantastic space because it has so much structure. So here I have the free loop space N, and there we have, let's say we have three interesting actions. So one is S1 action. Then we have the evolution. And then we have something a bit special. Then we also have it's not actually a group, but it's kind of a monoid. The monoid N is also acting on this free loop space. So yeah, so if we have R in S1 and V per loop, then the act by S1 action is just we reparameterize the loop. So R star is V plus. So this is always confusing, because when we make pictures, when we picture a loop, we never draw the parameterization. But this, well, the space we are working here is a parameterized loop. So if we want to when we visualize this, maybe we can do it like this. So we make here like this, and so we this gives us, say here we are at V0. So here's our starting point, and then this reparameterization is like here. So now here is the R. Now we start here. Then the involution is just going backward. So you could also take these two together, the S1 action and the involution. This gives you then an O2 action on the free loop space. The evolution is just going backwards, so we have minus of and then the action of the monoid is multiple cover. So we have if we have little n here, capital N, so we have n star b of p c n. So yeah, that's rather peculiar example. So of course we have many spaces with O2 action, but that we have an additional this monoid. This is rather special for this free loop space. And yeah, if you want, you can also take semi-direct product, and so we get the an action of the semi-direct product of O2 together with the monoid n on this free loop space. Now, so how does this Rabinowitz action function behave under all these symmetries? So for that, so Rabinowitz action function actually does not live on the free loop space, but on the free loop space times R. So we have to extend these actions a little bit to free loop space times R. So extend this action R. So we have here also one action. So if we R S1, so R star of out. So this is just we don't change the Lagrange multiplier, we just rotate the loop. So the involution, so we go backward. So we have b minus, but then we also swap the Lagrange multiplier. So tau goes to minus. And then the n action, the action of the monoid n star tau is just we act fusion on the loop, and then on the Lagrange multiplier will also be multiplied by n. Now, how does Rabinowitz action function transform under these actions? So we have first, if we just reparameterize our loop, Rabinowitz action function does not care, so it's S1 invariant. So we have AH of R star B tau. This is just AH S1. So what is rather special about this Rabinowitz action function is its behavior under this involution, because there it's anti-invariant. So this is kind of rather essential feature. So if we apply the involution to free loop tau, then we get minus. Okay. So this property, this is made this is related also to this state and this duality. Yeah. So yeah, this is so that's this anti-invariance on the time reverse. And then we have with respect to the monoid, it's transforming multiplicatively. The n star b tau, then it just gets multiplied by n. So that is the transformation behavior of Rabinowitz action functional under all these symmetries. And yeah, that's yeah, that also explains a bit why we can always go backward, and so that we have this invariance under Tyler's. Now, what is the little sibling of Rabinowitz action functional? Yeah, as I told you at the beginning. So if you this Lagrange multiplier, this Rabinowitz function is the Lagrange multiplier function. So instead of the Lagrange multiplier function, we could also look at the restriction of minus the area function to the constraint given by the mean value of h.
Urs, can I ask a question?
Yes.
So I'm very curious about this last thing about the behavior of the action with respect to coverings.
Yes.
Is there a formal reason why critical points, flow lines between covers stay within the space of multi-parametrized loop of multiple covers? Let me try to ask it slightly differently. I have two, threefold covers.
Yes.
I take a gradient flow line between them. Does that gradient flow line stay in the space of threefold covered loops?
Right. Yes. I have to. So for the gradient flow line, we need a chain, an almost complex structure. And if the almost complex, so it depends on. So if almost complex structure does not depend on time,
okay,
then you also have this behavior on the gradient flow line.
I see. And then do you also have some properties of the index of that gradient flow line?
Index is tricky. So you know all this work by long and index iteration.
Okay.
Because index here is index here is also the transversal Conley-Sender index.
Okay.
And this doesn't go linearly, but it goes like a quasimorphism. So, yeah, right.
So there's going to be some error terms having to do with.
Up to bounded error, it goes linearly.
Okay. Thank you.
So what is the little sibling? So let me abbreviate by a beautiful H from 3 loop space to R. This is just the map which takes the mean value. And so if 0 is a regular value of H, then 0 is also a regular value of the beautiful H. And then the constraint is abbreviated by like this LH. This is the preimage of beautiful H 0. So these are all loops of mean value of H mean value 0. And then the little sibling of Rabinowitz action function is just the restriction of the area functional to this constraint. So I write H. This is from H to R, and just V maps to minus the R. Now you observe the following thing, namely this is now hypersurface in free loop space. This is invariant under all these actions. So yeah, for example, if you reparameterize a loop, then the mean value of h does not change. If you go backward, it does not change. If you go n times around, it multiplies by n, but if it was 0 before, the mean value stays 0. So that means we can restrict all our actions to this LH, and then the little sibling of Rabinowitz action function has the same transformation behavior as Rabinowitz action function. So I can here I can just replace Rabinowitz action function by its little sibling. I have the same transformation. Yeah, so yeah, I like this Rabinowitz functional very much, but I have to admit it has a weak point. And so for why I actually I got interested in this little sibling is precisely because of the weak point of Rabinowitz action functional. And the weak point of Rabinowitz action function is, so we have an additional product on the free loop space. This is Chas-Sullivan product, and yeah, Rabinowitz action function does not behave so well with respect to this Chas-Sullivan product, with respect to concatenation. So let us look what happens with concatenation. So if we have two loops which start and end at the same point, then we can concatenate that. So we have so here V and then U. So concatenation of V and U. Just to hurry a bit, since you have to go off the time. And yeah, so this concatenation is usually not smooth, but it's continuous, because yeah. So maybe we replace this free loop space by the W12 loops. So we have actually a map from that we actually end in the same space. So replace this here by W12. So this is A1. And so now observe if we can look as well as hypersurface here in the W12 loops, namely the W12 loops of mean value A. And if you have two loops of mean value 0, their concatenation will also have mean value 0. So if you have here two loops which common end, starting and end point, so we have that this concatenation is still in this space. And how does how does the little sibling of Rabinowitz action function transform under concatenation? So it just transforms additive. So this is just Chas-Sullivan additivity. So we have a little sibling. If we look at if we apply it to the concatenation, so we just take the R minus area here minus area here. So that's just the sum. So this is a nice property of the little sibling. Rabinowitz action function here has its weakness, namely it has not such it's a bit hard to tell how it behaves under concatenation. First of all, because Rabinowitz function is not defined on the loop space, but on loop space times R, we also have to make sure, we also have to explain here transforms under concatenation. So that's the definition we have to do. So if we have two loops like here, with common starting and end point, then so we concatenate V and U, but then we have to specify what the Lagrange multiplier does. So the rho should now be somehow determined by the data V, U, and sigma and tau. And now, what we can try is we can just try to force this Chas-Sullivan additivity for Rabinowitz action function, and try to define rho in such a way that the Chas-Sullivan additivity holds. So we put AH sigma AH U tau. So this is now more a wish. So we would like that this comes that we have this formula. Now, so what condition do we get on rho? So you remember this Rabinowitz action function consists of two terms. So we have first the area term. The area term, this transforms additive under concatenation. That's very good. But then we have also this the Lagrange multiplier term. So if we want this equation, this gives us the requirement. So sigma mean value of H along V plus tau mean value of H along U. This should be rho of the mean value of H along V. So this row number 2, mean value of h along v plus the mean value of h along v. And now this forces you, this gives you a formula for a row. So there is, if we want this, then there is only one choice how we define row, but this choice is not always possible. So if we look at the formula for a row, this would be sigma integral, so the mean value of h along v plus mean value of h on 2 divided by sum of the values. You see, we should never divide by 0, and if these two sum up to 0, then this is problematic. So this is somehow the point of the Rabinowitz action function. This behavior under concatenation, and this has also some kind of concept, because as far as I know, nobody really defined products on Rabinowitz Floer homology, but when products are defined, they are defined on homologies which are isomorphic to Rabinowitz Floer homology, like V-shaped symplectic homology by Silva-Guancia, or Floer homology on extended phase space by Abondant-Olomeri. But yeah, not directly on Rabinowitz Floer homology, and because as a my worry about is the following. So what I would like to preserve is definitely this time reversal, probably that time reversal on the as that anti-invariance on the time reversal. So if you go to isomorphic homology, you still have on homology level, but you lose this on chain level. So that's why I become so interested on this little sibling, because it has both. It has the Chas-Sullivan additivity, and it has the anti-invariance on the time reversal. So what I recently proved is a theorem which tells us that there is one-to-one correspondence. If in a special case, if you just work on a symplectization, on a symplectization, there is actually one-to-one correspondence between the gradient flow lines. So as I said in the beginning, about this adiabatic limit. So in the symplectization, you don't need an adiabatic limit. So there is some in the symplectization, you can use R invariance, and then at the end you have to solve a custom-Warner equation. But this is a very nice equation. It has always a unique a solution exists and is unique. So that's what I recently wrote up is a proof that on the symplectization there is one-to-one correspondence gradient flow lines. And what I hope now to achieve in future with some kind of adiabatic limit is that even if you go out of the symplectization, that we have this at least for small epsilon, we have one-to-one correspondence between the gradient flow lines of the two functions. Right, and now I see time is over. So thank you very much for your attention, and then I stop here.
Thank you. So questions for Urs?
Can I ask a question? So
Yeah.
you talked about the product, but there's also the co-product.
Yeah,
So,
right.
like how does, actually I'm a little bit confused about what to think there, because that requires, because the pictures look very similar. Both pictures look like you have two circles come together.
Right.
But I think maybe there's a question of, in the case of the product, you're imagining that you glue at the base points.
Right.
And in the other one, you have a loop and it has some base point and it runs through itself at some other point, maybe. And, you know, is it possible? I mean, would you expect that, again, in the hypersurface case, the action is just the sum of the actions?
Right. Yes. Yeah. Right. I would expect. Yeah. Yeah. That's a good point. The co-product. Yeah. I would. So maybe right. So maybe we can, because what so what I have more in mind is at the moment it is some kind of Fukaya category with time reversal, some kind of Tate version of Fukaya category, so that you can so that you can go backward and forward. And then because then you just put some Lagrange in boundary condition, and then you you also have this Chas-Sullivan additivity. So this is of course an important property. And then one would expect that Hochschild, some kind of Tate version of Hochschild homology, gives Rabinowitz, and cyclic Tate cyclic gives equivalent Rabinowitz, and right, and then you then you can also express these co-products there.
Yes, but if I remember correctly, the co-product requires some additional structure on the category in order for it to exist. I mean, Sheila is nodding, so I must be saying the right thing.
Yes.
Right. So you need this. How is it called? This.
Calabi-Yau.
Calabi-Yau. Right, it is Calabi-Yau property. Yes. Maybe it's too early to say something about Calabi-Yau. So actually, I came a bit from a different perspective. So I was more coming from the semi-classical analysis of semi-classical physics, because the semi-classical physics is very much relies on these Feynman path integrals. And now this is of course a scary thing for mathematicians, but the results are too beautiful not to believe. And so that's why I was got very much interested in to replace these path integrals by the Fukaya category. So right. And now I cannot hear you anymore.
I think I mean, that sounds fascinating, but I'm not sure you can explain that in a few minutes.
No.
How the Fukaya category is supposed to replace the path integral. So maybe I'll just pause.
This is right. This this is maybe a bit long-term perspective. Right, and yeah, and then this Calabi-Yau should all, yeah. I cannot tell you yet at the moment what the Calabi-Yau. Yeah, but maybe Gilles has already some intuition about the Calabi-Yau property.
Yeah, I mean, certainly in the well, I mean, we can discuss more. Happy to discuss more. Maybe some.
Right.
Well, I don't know if somebody else has a different question, but I have a different question.
Yes.
This failure in the Rabinowitz framework for the action file internal to be additive under concatenation.
Yes.
So this must tell me, because this must tell me something about the isomorphism between Rabinowitz and symplectic, kind of destroying the action values, right? Because on the symplectic side, the action value.
If you go to this V-shaped,
yes.
So what you lose is this anti-invariance under time reversal.
Okay.
So you still have it on homology, but not on chain level anymore.
Okay.
That's what you have to pay there.
But again, so on the symplectic side, on the symplectic homology side, the pair of pants product preserves action.
The pair of pants preserves action, and so that was also in this extended phase space homology of Abondando-Lomery. So that it is this trick. So you have instead of looking at M, you look at M at cotangent bundle of R, and you look there at the Fleur homology there.
Okay.
So there and there you have the usual Fleur homology with usual pair of pants. So you also have a Chas-Sullivan additivity, but there you also lose time reverse under going back in time.
I had a related question, which is that, so in the finite dimensional model, you know, there's this fact that everything coincides up to an index shift by 1, right?
Yes.
Of course, if you transfer the pair, you know, that means if you transfer the pair of pants, like so the Morse tree product on the hypersurface to the sort of index +1, it won't be a degree 0 map anymore. It won't be the usual pair of pants product. Is this sort of related to the failure of additivity? Am I supposed to think, you know, the usual degree 0 product?
So this great. So in the original paper, we had our grading was half integer valued, and somehow I still think this is kind of the most natural grading in Rabinowitz Fleur homology. So there is actually some philosophy. So if you think of this Conley-Sender index, you can think of it as of half signature index. So if you have right. So you have infinite Morse index is infinite and Morse coindex is infinite, but the difference is somehow finite. And this half signature index, this is on even dimensional spaces is integer valid, and on odd dimensional spaces is half integer valid. And we are at the space we are here is on loop space times R. So the loop space is kind of, I still think of it as kind of even dimensional space because it's symplectic. And then we have the R. And so, and the same thing happens for the little sibling. And so we have also one less than, and actually these half integers, this half integer index, this is also in finite dimensional. There is no index shift because this because you have precisely this justness that you have
the Hessian has always one additional positive eigenvalue and one additional negative eigenvalue. So the half index, the half signature index does not change. So of course, in Morse homology we prefer to use the Morse index because we prefer to start in degree 0. But there is we could start again also with the half signature index, and we would just have a shift of about the half dimension of the manifold, and this will not change at all. So I would still think that maybe one should this half integer values have somehow Rabinowitz prefers this. Of course, if you want to compare it with symplectic homology, this is not good. So there you have to go to integer values. Then we did a global time shift, a global shift by 1/2. But yeah.
How do you deal with signs and operations if there's a shift on one hand? There's an integral shift.
If there's
like if you have a product, how do you say the product is commutative, graded commutative if things have integral degrees?
Yeah, right. It's I will say 2 there is no issue, but
okay,
but with right. So right, you get.
I mean, you could introduce. Well, maybe we should stop. This is another question.
Yeah, right. Yeah.
So can I just ask, so like, I'm just trying to understand because you mentioned this kind of desire to get like chain level data. So like, what would the expectation be that somehow, like, if you do this little sibling Rabinowitz flow homology, then so the pair of pants product, sorry.
Yeah, right. So right. So I don't think that little sibling alone. So I don't say just replace Rabinowitz by little sibling, because both together should be strong. So the little sibling has this nice two nice properties, but for example, what's not so nice for the little sibling is the space where it lives now depends actually on age. Where in Rabinowitz, you're on the big space, so you can homotop. So if you want to go for invariance, then the invariance is much better for Rabinowitz. Now I'm not so confident about Rabinowitz for the Fukaya category, so if you compute out the Fukaya category things like Hochschild homology and cyclic homology, this should have this should be the same in Rabinowitz, and this should be invariant. But then the age invariance of Fukaya categories is not so clear, but still, for in the semi-classics, so you have fantastic relations between different equivalent homologies, and so you can't directly go from one to the other. So it seems that you have to have some Fukaya category in the background where you can relate these two. So this you have to do for the little sibling, and then you look at the via the Adiabatic limit. Then if you compute out something out of this Fukaya category like Hochschild homology, then you get something on Rabinowitz flow homology, which does not depend on age.
I see. I see. So somehow is it sort of would you expect that, like, by thinking about this little sibling, that you can sort of find this kind of additional structure, like some chain level filtered thing with involution that you could see on?
For Fukaya, right? For if you want to have Fukaya category with time reversal, there you should have Chas-Sullivan additivity. And this is problematic on the Rabinowitz Floer homology. But if you compute something out of Rabinowitz Floer homology, which which make Fukaya category, which makes sense in Rabinowitz, like like Rabinowitz or equivalent version of Rabinowitz Floer homology. There you don't need to worry about this failure of Chas-Sullivan additivity.
I see. So maybe let's thank Urs one more time, and then if anyone wants to stick around and ask more
Thank
questions.
you for organizing this. Thank you.
Thank you very much for really interesting talk.